Guys, welcome to my YouTube channel. Today we're gonna continue with our chemistry series of electrochemistry. Now, on the first part of electrochemistry, when I ended the video, I explained these two half reaction equations. However, I did not explain why these two reactions are the ones that are likely going to occur instead of, let's say, for instance, copper releasing two electrons to form part of the solution. I just want to explain why zinc is most likely going to lose electrons. So we're going to go to the table, the redox table, whereby we will have to, if you check here, there's a column of potential differences for each and every reactions. So the reactions that we have a copper reaction and we have a zinc reaction right there. Now, let us check their potential. If you check the potential there, this one is positive 3.4. So this, so copper reaction is most likely going to go in a forward direction because the value there is positive, or that value is bigger than the value for zinc. Where is zinc? Yes, zinc is minus 7.6. All right. Now let us go back where we were. So zinc is most likely going to release electrons because of its strength. I mean, if you check from the table, it has a negative value, meaning the reaction will take place in an opposite direction. So zinc will lose 2 electrons, as you can see. All right. Moving right along. I don't know why this is crazy, guys. All right, that's what we have. Now, electrolysis. Now, with electrolysis, I'm going to give an example of electrolysis. Let's say, for instance, I mean, in industry, you would find guys from the industry wanting to split the following chemical, this chemical. Yeah, guys, I don't know why I'm having a problem. I just want to solve this problem for you guys. Okay. My pen is not working properly. My pen is not working properly, guys. Guys, please like and subscribe so that I can buy you guys a new pen. Right, I think it's functioning now. Let me just erase all these marks. Now, electrolytic cell also has equations that takes place within that one compartment. Let's say, for instance, in the industry, if they want to split that chemical compound, what they can do is that there will be two half reactions. We will have the following. we will have copper chloride dissociate. It will dissociate, of course. It's an aqueous plus 2 chloride ions. That's aqueous. All right. The first half reaction that we are expecting is the following. We are expecting a copper plus 2 electrons to go and form a solid. This is a valuable product, isn't it? It is. But I'm gonna show you guys the reason why these equations are gonna need are not spontaneous. I'm gonna explain to you guys. Now, this is the first half reaction. Right. Second half reaction, we're gonna have 2 Cl negative negative, releasing the electrons, 2 electrons plus Cl2. Chloride are balanced right there. Okay, this is the second half reaction. Now, if we go to the table of potentials, we will have, where is copper? Yes, we have copper. No, the first reaction that I did was we had this solution, and what happened is that copper gained 2 electrons, and the potential difference was 0.34, if I'm not mistaken. Let me go and check again. Yes, 0.34. Now, the potential difference for, where's the chloride equation? I just want to show you guys something. Guys, please pay attention on this one. Yes, now we've found it. Now, what we know is that, okay, this equation it has a potential difference of 1.36. This one has 1.36 voltage. Now, what you will notice is that because this one has high potential, it means for a spontaneous reaction, this should be a forward reaction as per the reduction table, because it has higher potential. But let us see, this should be a forward reaction. However, for us to split and produce chloride gas, we need to reverse that equation. So in order to reverse it, it means we will need energy, because things are not going on normally. We will need energy. And also on the copper side, this equation was supposed to go in a reverse direction, but it took place in a forward reaction. Therefore, we need energy. That's what I wanted to explain to you guys, because during electrolysis, you need energy to activate the two half reactions. All right. Now, what are the applications of electrolysis? Okay, the first one is extraction of metal. There we were able to extract copper, and also we were able to extract a valuable gas. Also in the production of gases, all right. And also it is used during electroplating or coating. Those of you who have gold earrings and silver earrings, they were electro coated. All right, coating, that's not the correct spelling. Coating. Okay, I hope that helps. Now, moving right along, we're gonna talk a little bit about photovoltaic cells. Now, what we know about photovoltaic cell is that, or the galvanic cell, what we know is that at the anode, is a stronger reducing agent. Okay. Now, on a galvanic cell, we have the so-called salt bridge. Now, with the salt bridge, it completes the circuit. And also, it keeps two electrolytes separate. And typically, these are the typical salt bridge chemicals used. Or KCl. Usually these are weak reducing agents. Okay. Why are they weak reducing agents? They are weak reducing agents so that ions are not oxidized, but rather the ions in the electrolytes are the ones that are supposed to be oxidized. That is why. Now, what we know about the current is that electrons, they move from anode to cathode. Okay. Through the conductor. Okay. Now, there's a so-called the cell notation. that we must master. Now, with the cell notation, we start the cell notation has the following symbols. That is the salt bridge. Okay, so what we know is that at the salt bridge, what we know is that when we write the cell notation, we start by oxidation, and then reduction. Now, with oxidation, zinc solid loses electrons. Then it becomes, and then those electrons are gained by, they are gained by copper, which is inside the solution, and then it becomes solid. We must always write the phases or the states as, okay, that's what happens in the solid cell notation. Now, to calculate the EMF, we know that the EMF of the battery, it will be E at the cathode minus E at the anode. Where do we find these values? From the reduction table. Now, what are things that can increase the voltage? We have the surface of electrodes. We also have concentration of electrolytes. And note that when the reactions reach equilibrium, the cell dies, or the battery dies. Okay. Now, I think that is all. Now, guys, thank you for participating, and see you guys in the next one. And guys, please don't forget to like, subscribe, and comment in the comment section. I'll see you guys in the next one.